All right. So today we have Hamza Ahmed, who will tell us about who will explore with us T-duality of little string theories. Take it away.
Thank you. First of all, I'd like to thank Julius for inviting me. Over the past year, I've listened to a lot of really nice talks at these meetings, and so it's great that I'm finally able to give a talk of my own here. So today as Julia said, I'll tell you about some of the recent work that we've been doing regarding the T-duality landscape of little string theories. Then don't worry, I'll explain what each of these words mean. So this will be based on some work that I've done with a permutation of these authors. So these first two papers were with my advisor Fabian Ruhle and Paul Constantin Oman. And this upcoming paper, hopefully in the next month or two, will be with Florent Baume and Paul. So before I get into it, let me sort of motivate why I find at least little string theories very interesting, and maybe why you might also find them interesting. So we know that quantum field theories have this feature of global symmetries, which in recent years has been, well, now it's been 10 years, has been sort of generalized to these higher form these higher form variants. And so yes, and whereas on the other hand, gravity, or at least one of the lessons that string theory teaches us about gravity is that theories of gravity have this feature of T-duality, where what I mean by T-duality is that if you take two theories of gravity that are very different looking in some dimension d, once you reduce them on some compact manifold, you essentially get the same theory. Famously, though.
And I'm very sorry for the early interruption, but like a free scalar has T-duality. So I also saw this sentence in the abstract. I don't understand why you say that this is gravity property. Like it's field theories have T-duality.
Sorry, which field theory are you talking about?
Free scalar, free periodic scalar. I mean, eventually, I do think it's just semantics, and like, please go on.
Yeah.
But
I guess what I mean by T-duality is that there are these, like in the Ploczynski volume 1 sense, that you can sort of exchange momentum and winding modes.
yeah, this is one example, but okay. I mean, I
Yeah,
really
that's
think it will be principal, but I don't think it's a gravity-like property. Okay, thanks.
Sorry, can I make a comment? So, you're meaning a different thing. In string theory, T-duality is a property of the bulk spacetime. When you talk about T-duality and the compact boson, it's like the T-duality on the worldsheet. There is a property of quantum field theory, but it becomes a property of string theory in the bulk. So what I think what he means by T-duality here is T-duality in the bulk, the property that the theory on a small radius is equivalent to the theory on a big radius. And this is not a property of quantum field theory.
I think it's
that's
between two quantum field theories. But okay, I mean, let's
stop this for now and let's crack on.
Yeah, no, this is a good point. I mean,
let's just not worry too much about how we define T-duality. We can talk about this at the very end.
Just as a comment, Guillermo, just read the Zyberg when he first proposed this, and you'll get all of the answers to the questions. Okay, go on.
Thank you. So good. Thank you for the discussion. Yeah, good. But famously also, we know that sort of using black hole arguments and other string theory arguments, we believe that sort of any putative global symmetry we may think exists that exists in a theory of gravity must either be gauged or broken. So then one can ask the question, are there any theories, consistent theories that one can write down which sort of have both these properties, which have this property of T-duality, as I've defined it, and global symmetries? And so indeed, these kinds of theories are sort of the subject of this talk, which are these 60 supersymmetric quantum field theories which are known as little string theories. And so in particular, today, the global symmetries of these theories that I'll sort of focus on are these, what are known as two-group symmetries, which I'll explain as we go on, and the conventional flavor symmetries, or this the zero-form symmetries. On the other hand, what I will the T-duality that I'll consider for these theories is only up to is only a compactification on a circle. So what I'll think about is two distinct 60 little string theories, putting them on a circle, and then checking if they lead to the same 5D theory, which would be a T-duality in one more dimension. So good. So this is sort of like as you can see, that these theories sort of form a nice middle ground, a nice middle testing ground between full-fledged quantum gravity theories and quantum field theories. And once this is with this, now one can sort of ask a bunch of questions, and which may be also easier to sort of tackle than if you sort of, for example, tried to tackle them in a gravity theory. So one of these questions that we've worked on extensively, and a lot of other people have as well, is sort of the structure of the duality map. So how can you sort of give some order to the kinds of theories that you have. And then the other question that one can ask is, are there any invariants that I can identify on both sides of this proposed duality that sort of must match for there to be necessary conditions, if you like, for two theories to be T-dual. And so I'll touch on both of these questions in this talk. With that, let me sort of give you a brief outline, a very modest outline. Because I know like little string theories are not necessarily at the forefront of everyone's mind. I'll sort of introduce what little string theories are from a field theory perspective. Then I'll move on to what are known as heterotic little string theories. These will be the focus of this talk. Then I'll explain what we mean by T-duality of little string theories and how one sort of identifies T-dual little string theories and so on. And then I'll sort of get into the sort of the recent stuff that we've been working on, is basically arranging these theories into these nice orbits. Then I will give I'll give a conclusion and an outlook. Good. So what are little string theories? So as I said, that I'll be focusing on heterotic little string theories. So these are minimally supersymmetric 60 theories. And so before I get into that, let me just introduce minimally supersymmetric 60 theories in general. So if I have, like the supersymmetry algebra in 60 allows for tensor multiplets. And so if I have at least one tensor multiplet, then I can have an associated pairing matrix for the BPS strings in the spectrum, which couple to the B fields in the tensor multiplets. And so this pairing matrix is sort of akin to what you have in 4D for monopoles and electric charges, but in 60 you have this sort of pairing for strings. And it turns out that the determinant of this matrix tells you the determinant of this matrix tells you the UV completion of your theory. And what I mean by that is sort of one can sort of think of it a bit intuitively, in the sense that we know that any gauge theory in greater than 4 dimensions is non-normalizable. However, when you have supersymmetry and you have these tensor multiplets, because of supersymmetry, the gauge coupling is actually inversely related to the tension of these strings. And so when at really high energies, when the gauge coupling blows up, at the same time you have these tensionless strings appearing in the spectrum, which then provide you with these new degrees of freedom that UV complete your theory. And so there's 3 kinds of UV completion that we know of in 6D. One of them is, of course, the SCFT, the superconformal field theory. Then it's the little string theory, and then of course we have the supergravity theory. And in particular, for the first 2 of these, the gravity multiplet is decoupled. And so this is sort of this is the reason why sort of you know, that yeah, so the gravity multiple is decoupled for the first two. However, the little string theory, much like the supergravity theory, has this intrinsic scale, which is known as the little string scale, and it's like the Planck scale for supergravity theory. And this is why sort of, again, you see that these theories form a nice, you know, middle ground between the gravity theory, i.e. supergravity, and the field theory, i.e. The SCFT. Another important, yes.
So you have two labels, I and J. What's the range of these labels?
Oh, good. Sorry. Yeah, these are, yeah, this is the number of
Tensor?
Tensor multiplets, yes. Yes. So
And
this includes,
if you have one tensor multiplet, then the eta could be positive, negative, or zero.
Good. If you have one dynamical tensor multiplet, yeah, then it would be, yeah, it could have a determinant. Yeah, it could be just the zero self-intersection, right? So eta II equals 0. It could be greater than 0. It could be -1 for supergravity.
I see. So SU2 with 16 flavors will be in this family, according to this.
SU2 with 16 flavors would have 0 dynamical tensor multiplets, right? So it would have no. I'm only considering theories with at least one tensor multiplet.
There would be one tensor for the SU2 coupling.
Yeah, I would count it as one.
Right. Yeah, good. Sorry. Yeah, sorry. You're right. Yeah, you need that to cancel the anomaly. Yes. So yeah, in that case, yeah, you have one tensor.
One, but how do you see that it has zero pairing matrix? You need some self-intersection, which is 0. I see.
Yeah. Exactly. I mean, I'll show you like explicit examples.
Okay, maybe I shouldn't. Yeah, thank you. Yeah.
Yeah. I mean, there will be actually the specific example that you're talking about. I'll show you. Yeah.
Okay.
Good.
Paul had a comment. Maybe we can just quickly do this. If you want to mute yourself and say it is also good.
Oh yeah, sorry. Yeah, it's so just a quick thing. So the IJ goes, let's say, from 0 to the number of tensors. So if you usually it goes from 1 to the number of tensors, but if you normalize it from 0 to the number of tensors, it's not exactly the number of tensors plus 1. And yeah, the eta IJ is as he wrote, the pairing matrix should be semi positive definite, so it can have 1, 0 eigenvalue. And there's one example precisely where the eta IJ is exactly 0, and that is the t equals 0 case. So no tensor multiplets. Yeah. And then the anomaly must be cancelled by itself.
Okay.
Yes,
good.
Thank you. Yes, thank you.
Thank you for the comments. Yeah. So yeah, as I was saying, like the for the little string.
Sorry, Craig now also wants to
type
in.
I don't want to derail anything, but the comment Paul just made is very confusing to me. So if I take the E string, a single -1 curve, that's one tensor. You say that the pairing matrix is a 2x2 matrix?
No. In that case, 1 by 1. I think what Paul means is that I can start with an n by n matrix, and if that tensor has no 0 eigenvalues, then all of those are dynamical. If it has a single eigenvalue, then you get a little string theory.
Sure, but then you also have another tensor associated to that thing. It's just you don't.
It's not dynamic.
One of the tensor branch should make it become associated with some tensionless string, but it's still a tensor.
Yeah, but it's not a dynamical tensor, right?
Sure. On the tensor branch.
There's always a linear combination which is non-dynamic.
Right. Sure.
I think that's what maybe Paul meant.
Okay, but then I don't know what he means in the Sucre case. I feel weird. Sorry. So in the Sucre
No, no,
case, the same statement, or do you want to make a different statement that you can have multiple additional entries in the matrix?
good. So for the Sucre case, it's there's this other constraint that sort of makes it there's obviously the anomaly cancellation for gravity, the diffeomorphism anomaly. So that basically constrains it to -1. I don't know the exact derivation of this, but this is just, yeah, this is in the original classification paper.
Okay, cool.
Thank you.
Okay, let's let Hamza continue. Thank you for fielding all the questions.
Good. So right. So as I was saying, that the determinant of this matrix, as we've now established, is 0 for the little string theories, which implies that there is a 0 eigenvalue. And this, again, as we'll see in the next slide, leads to a unique global symmetry for the little string theory that you won't find that you won't find in the SCFT or in the supergravity theory. It must be gauged or broken anyways. But yeah. So good. So now let me sort of finally, because this is the Quiver meeting, let me introduce how quivers enter our story. So as I was saying, that you have these tensor multiplets in your theory, and these have a B field, and they also have a scalar, to which you can then give a vev in such a way that you don't break supersymmetry. So giving a vev to these scalars does not break supersymmetry. So, and then you move on to what's known as the tensor branch of the theory, because this vev also is related to the tension of these strings. So you now have tensionful strings on the tensor branch of the theory. And so on the tensor branch, you can actually write your theory as a quiver gauge theory. So here is the notation that I'll use. So you will have the gauge algebras here, the GIs, and the associated tensors, or the tensor multiplets, given by the self-intersections Ni. So here I've just labeled them by the self-intersections, and the diagonal elements for all these quivers are always -1. So they only intersect with the diagonal intersection is -1 for all of them. And then you also have, of course, some matter in the theory. So you have bifundamental matter, and you could have other matter that transforms under some flavor symmetry. And of course, we know that in 6D, we're strongly constrained by anomaly cancellation. So of course, I can't just pick any gauge algebra, any NIs, and any matter. You have to satisfy the anomaly cancellation. So up to this point, I have not said this is how you write down any 6D theory. I mean, this isn't specific to little string theories. However, now the specific case where I have a 0 eigenvalue for the matrix, I actually get another feature, another extra piece of data, which is that there's a non-dynamical two-form field in the spectrum now, which couples to what is then known as the little string. And the reason this non-dynamical two-form field arises is again because of supersymmetry. So because of supersymmetry, these etas actually show up as the coefficients of the kinetic terms for the B fields. And so if there is a 0 eigenvalue, then we know that you can always find a basis for the B fields such that, the kinetic term for one of these linear combinations vanishes. And so if that linear combination vanishes, then you know that the B field is no longer dynamical. And so instead of being a gauge field now, this actually generates for us a U1 global one-form symmetry, which is not present in the SCFT. And this global one-form symmetry can then be written down as a linear combination. This is the specific linear combination, and the coefficients of this linear combination are what are known as the little string charges, under which the strings are charged. Good. So now, I mean, this was just a field theory sort of review of what 6D theories are and what little string theories are. But now let me just focus on the specific kind of little string theories, which we'll look at, which are the heterotic string theories. And so as the name suggests, of course, these have something to do with the heterotic string. And we know that there's two kinds of heterotic string. And these theories arise as the world volume theories of the NS5 branes in these theories, of a stack of NS5 branes in these theories. And another piece of data that you can assign to these theories is the transverse singularity. So if these NS5 branes probe these NS5 branes probe some C2 mod gamma G type singularity, you can associate the label G to these theories, where gamma G is the is a subgroup of SU2, and the G is in correspondence with the ADE classification. And finally, there's another piece of data that one can assign, which is the sort of a boundary condition for the E8 times E8 bundle of the heterotic string at infinity. And this flat connection essentially is classified by these group homomorphisms of gamma G into E8. And from these were classified by Frey and Rudelius in 2020. But from the field theory point of view, all this choice gives us is the flavor symmetry of our theory. So if I pick a trivial choice for these flat connections, then I just get the full E8 times E8 flavor. But if I pick any non-trivial choice for this flat connection, then I get breakings of this flavor symmetry. Before
a question. So will you get theories with single gauge groups as part of this family? Like, I don't know, G2 with 10 flavors, SU3 with 18 flavors. Those will sit in here?
Yeah, good. So at low enough M, so if M is 1 or something, if it's only a single 5 brane, then you can have weird quivers with, like you say, like you don't have any ADE algebra there. But for high enough M, you do get G2 F4 and all these kinds of algebras, but it's always sort of, a part of the conformal matter chain.
Yeah, but is there a way to isolate them such that I'll get this?
Yeah. So you're basically saying if you can get like a G2 on a zero curve or something.
Yes. So then I have G2 with 10 flavors, and I just focus on this theory, single gauge group and a little string.
Yeah. Good. I don't know if they have a heterotic construction, but I mean, if they satisfy the anomaly cancellation, that's a little string theory. But I don't know if they have a heterotic construction.
I see. Okay. Do you also consider SO32 heterotic theories?
Yes, it will be. I mean, it won't be the main subject of this talk, but I will introduce it in the next slide.
Okay. Thanks.
Thank you for the question. Okay, good. So yeah, before I sort of go on, let me sort of introduce like another way we can look at these theories, which is in the Horzawa-Witten picture, using heterotic M-theory duality. So for the trivial flat connections, you get the following picture. You have now the LST arises as the world volume theory of M5 branes, probing again a C2 mod gamma type singularity with M2 branes stretching between the M5 branes, which of course then lead to the strings in the spectrum. And then of course you have the M9 branes with the full E8 times E8 in this case. And so in the quiver notation I introduced earlier, this is the quiver you get. You basically get this 1, 2, 2, 2, 1 form with these gauge algebras here, and you see the E8 times E8 flavor. Note, this is not the full tensor branch of the theory. This is what's known as the partial tensor branch. So for every E8 times E8 LST, the partial tensor branch is the same. The full tensor branch, however, depends on what G is. So what can happen is if G is if for certain G's, what can happen is that the M5 branes can fractionate. So then this quiver can actually become bigger. So you get more curves and more strings and more curves and with more of these algebras. But I'll show you examples of when this happens. But here, just the fact to remember is that the partial tensor branch for any E8 times E8 LST is the same. Good. Okay, good. So as as we just said, so this was the E times E heterotic LST. Now we have a similar story for the SO32, of course. Now, of course, the flat connections are classified by this homomorphism. So group homomorphism from gamma G to spin 32. But we have the same story, but in this case, however, the shape of the quiver is actually the affine Dynkin diagram of G, or its foldings. And this was first, I think, seen by Introligator and Bloom. And to just give you a flavor of what happens here, for, let's say, the E8 singularity, you get the following quiver. So this is the SO32 LST with the trivial flat connection chosen. So I have the full SO32, and G is equal to E8. And so you can see this is the affine E8 Dynkin diagram. For other singularities, as I said, you can also get foldings of these. So for example, for the SO4n plus 2 type theory, you get the folding of the spinor and the co-spinor nodes. And here, another thing to notice is that the dependence of M is actually in the rank of the gauge algebras, which of course was not the case in the E8 times E8 LST. Good. Right. So now, yeah.
Yeah. So here in this family, if you take,
Yes.
if you can go back to the previous, where is this? The SO32.
Yeah.
So if you take M equals to 1 and gamma
Yes.
to be trivial,
Yes.
then you get SU2 with 16 flavors, right?
Here on the SO32 side, you said G, so what's the singularity?
Trivial. Gamma is trivial, so it's just C2.
Okay, gamma trivial. Okay,
and
good.
M is equal to 1 for simplicity.
Yes, exactly. I was actually, this example is actually in 2 slides.
Very good. Thank you. Okay.
Exactly. Very good. So yeah, as now that we've sort of given a precursor, let's talk about the T-duality of LSTs. So to talk about T-duality, we first need to talk about putting these theories in a circle. So if I take a 60 little string theory, I put it on a circle, I get generically some 5D Kaluza-Klein theory. However, now, because, of course, this theory has global symmetries, as we just talked about, you can actually turn on certain data associated to these global symmetries, right? You can switch this on along the circle. And of course, one of these is just the Wilson lines for the E8 times E8 or the SO32, which generically would break these algebras. However, you can also have discrete symmetries in your theory, right? And so if you have discrete symmetries, we can also switch on discrete holonomies or discrete Wilson lines for those symmetries. And in that case, you get what are known as twisted theories in 5D. So in particular, the discrete symmetries that we can have are associated to the outer automorphisms of the gauge algebras, right? Remember the gauge algebras in our quiver? So they have an associated, generically, I mean, they're subtle. Of course, you have to consider if the matter in the spectrum behaves nicely under the outer automorphism, but generically you would have some discrete symmetry associated to the outer automorphism of the gauge algebra. And if you then turn on a discrete holonomy for that, you would get twisted algebras in 5D, which will be labeled as this, where n is the order of the twist. There's another discrete symmetry that you can have, which is essentially associated to the symmetry of the quiver itself. So if the quiver is symmetric about some axis, then you can also twist by that discrete symmetry. So again, these are just different things that you can do on the circle, so as to get interesting 5D twisted, untwisted theories. For the gauge algebras that we were just talking about, for the twistings of the gauge algebras, you have the following choices. Of course, like these are the gauge algebras with non-trivial outer automorphisms. So you have, so generically you would have some discrete symmetry in your theory associated to these, and then you can sort of twist by them. But yeah, the point is sort of like, yeah, you have all this data which you can switch on along the circle. You can choose not to switch it on. And then the statement of T-duality basically says that if I take one theory, I take another theory, put it on a circle, switch on stuff here, put it on a circle, switch on stuff here, I get the same 5D theory. I haven't told you what I mean by same yet, which I will in a couple of slides, but or at least the necessary conditions we think need to be true for them to be the same. So now finally we can get to the example that
there was a raised hand by Mario. There is a
Yes.
raised hand by Mario.
Yeah. Hello, Hamza. Sorry. I just had a question about the elite string theory that you showed before in 6D. What is confusing for me is that if I really look at the quiver that you draw, like with the two E8 node at the end and some G in the middle,
yeah. Let me just get to
how
this.
can I, is there a way in which I can immediately tell, oh, well, this is not some conformal matter of type E8, and instead is a little string theory just by looking at this quiver?
Good. So you can write down the Dirac pairing matrix. So if it's just conformal matter, which is SCFT, right? The Dirac pairing matrix would have a determinant that's not 0, right? It would be greater than 0. So from that you can just that's the simplest way to just tell that this is not an SCFT or
Okay.
like conformal matter. Yeah.
Thank
you. Good. All right, so yeah, we finally get to the example that Amihei was talking about. You can the most simplest example is the world volume theory of m+1 ns5 branes with a trivial G and a trivial flat connection. So in this case, on the E8 side, you just have these tensor multiplets. You have no gauge algebra, but the dual, the SO32 dual, is actually the SPM gauge theory with no tensors, as it was no dynamical tensor, and 16 flavors, which then transform as under half hypers of SO32. And so this is a very famous, if people remember, this is sort of a very famous SP factor, which Witten, I think, first found in the full heterotic in the full heterotic string theory. This was sort of the non-perturbative gauge factor gauge symmetry that you had at the core of the SO32 instantons. So this is the realization of that same fact, but for the little string theory. Good. So again, I keep saying these are dual, but I mean I haven't told you why they're dual, and now we'll sort of get to that fact. So
before you go on there, you actually haven't yet told us which two theories you're talking about. So the 1-2-2-2-2-2-1 corresponds to something like m different LSTs. Do you have something to say about which one in particular is going to be T-dual to the single zero curve LST?
Oh yeah. I mean, sorry, maybe I should have made this clear. So this M factor is the SP is it depends on how many instantons were there on the other side, or the number of 5 branes. So M equals 1 would be
the question is, I have m-1 instantons or m instantons on the left-hand side, and I can choose to put some number of them inside of the left E8 wall and some number of them inside of the right E8 wall. And the different choices of doing that correspond to different LSTs.
I see what you're saying. Yes, you're basically saying that when I blow down everything, I get to a point where it's like 1, 1, and then if I choose to blow this one down, I get a different LST as opposed to this one.
Right. That's the geometric theory,
So the question you're right.
About which particular combination is the thing which is T-dual?
Yeah, that's a good question. I don't have anything super deep to say about that sort of subtlety. I basically look at these theories on the full tensor branch. So what you're talking about is sort of, on the full tensor branch, these are the same, right? Do we agree on that?
I mean, on the full tensor branch, you're not talking about little string theories. You're talking about just quantum field theories of free tensors and stuff. So
Yeah, good.
I'm not sure I'm super happy with that statement. The statement could be that there is just one particular choice which maybe ends up being T-dual, but it would be nice to know
Right.
if there's someone if there's someone who can tell you
Yeah,
that answer.
that's a good question. I don't have anything to say about that really.
Okay.
Yeah, like which choice I'm making here that corresponds to the SPM.
Right.
Yeah. No, that's a good question. I have.
You don't have to hit any of the walls, right? You could also just combine the limit 5 branes, keep them in the middle. Maybe that's where we are. You see what I mean?
That wouldn't give you an LST.
But okay, maybe. Oh, I see.
To get an LST, you need to decide.
Okay, I see. You have to pick a wall. Okay, thank you.
Yeah, good. Right. Right. I mean, the way I'll define the LSTs in terms of the T-duality invariant data, that data is the same regardless of the choice I make. So maybe just take that as the definition. Good. So of course, if I want to identify some T-dual theories, and I've already told you that these theories are more like field theories than gravity theories, then you can sort of look at certain field theory data that must match for any putative T-dual. So the first thing that just from field theory that you can sort of say is that the moduli of the 5D theory, that once you sort of compactify the 6D theory, like the moduli of that 5D theory should match for any two putative T-duals. So one, of course, in 5D, the moduli include the Coulomb branch, the dimension of the Coulomb branch, which of course is given by this 6D data, which is the rank of the gauge algebra plus the number of tensors, because now you can reduce the tensors on the circle and get gauge fields, U1 gauge fields. And then the other piece of data that you have is the dimension of the flavor Wilson lines that you can turn on along the circle, which is, of course, just the rank of the flavor algebra. So these two are just moduli that need to match for any putative T-dual theories. So this may be obvious, right? This matching is probably very obvious, but the second is sort of the cool thing I think about little string theories is the two-group symmetry associated to these theories. So this two-group symmetry is essentially a mixing of the one-form symmetry that I introduced earlier, which is unique to LSTs, and of the zero-form symmetries in the theory. And in particular, the ones we'll look at are the Poincare and the R symmetry, right? Because this is a Poincare invariant theory, and it's a supersymmetric theory with some R symmetry. And so this two group data is encoded in these two group structure constants, which are these kappa R and kappa P. So the exact form of these doesn't matter. You can just see that it depends on the little string charges, as it should. And then it depends on the dual Coxeter number of the gauge algebra and so on, but the exact form does not matter. But the point is that these should match, and the reason is that these coefficients also encode certain mixed anomalies of your field theory. So of course, if you want any dual theory, you would like that the anomaly polynomial for the theory must match. And so this is why these kappa R and kappa P are expected to match as well. I mean, there's no sort of proof, but these are sort of expected to match on these arguments. And yeah, so this is sort of just encoding this mixing that I talked about here. You can sort of think of this as a Green-Schwarz mechanism, but for a non-dynamical field, right? In string theory, you have these H's are dynamical, and then you have this Green-Schwarz mechanism, which cancels the gauge anomalies associated to the gauged R symmetry and the diffeomorphism. But in this case, these are all global symmetries. So right, this is the data we expect to match in 5D, but just based on field theory arguments. So one should think of these as necessary conditions, but they've not been proven to be sufficient. And I'll show you how we sort of use another another check, so to speak, to show that theories are really T-dual. Good. So then one can also ask what happens if you allow for these twists that I talked about. So the data I wrote down like earlier, or at first, was just for untwisted theories, and so we know that it was shown in these papers here that this matched, and then we sort of showed that so yeah, maybe a bit of history is good. So Del Zotto and Omori initially showed that the Coulomb branch kappa R and kappa P should match. And then these other papers basically verified that in multiple examples. And then we, in 2023, we basically showed that the rank of the flavor symmetry must also match. I mean, this was always expected to match, as I said, but there were certain cases where you had these ABJ anomalies and you had to take them into account. And once you did all that, one can check that the flavor also matches. Right, so when you now allow for twists, you can ask, okay, does this data continue to match if you allow for these twists? And indeed, we showed in our 2024 paper, where we constructed these twisted theories, we showed that once you do these twists and so on, this data, at least all the examples, and there were a lot of them that we checked, this data continues to match. So it seems like a good set of invariants. Then you can also, one comment about this kappa P, because I think it's a very interesting, invariant. So kappa P is actually was known to be 2 for all heterotic LSTs. And kappa P was known to be 0 for the other kind of minimal LSTs, the type 2 LSTs. And so the interpretation that was given to this in this paper by Del Zotto and Omori was that it counts the number of M9 branes based on these 2 data points. But we showed in our paper that actually kappa P can also be 1. But you have to allow for twisting. And so this involves these twists that I talked about earlier, where you fold the quiver. And so again, we did that, and we then computed the invariants, and again, everything matches nicely. And so again, these invariants are good invariants, whether it's twisted or untwisted, and so on. Is there a question? Okay. Good. So at this level, right, okay, I told you these are necessary invariants. And so how do I actually know that these theories are dual just based on this? And the idea, of course, is we always in these situations turn to a UV complete description. And so as I'll show you just a couple of slides of our construction. So the construction we use is, of course, F theory, which provides us with this UV complete description, and all these invariants are then just encoded to geometry. Good. So, right, before I obviously go into that, I would like so today as I sort of mentioned earlier, that we'll only focus on a subset of these dualities. We'll focus on the dualities between E8 times E8 theories, right? I mean, the canonical duality is, of course, the E8 times E8 and the SO32, but there's no reason why you can't just have dualities between E8 times E8 theories. And so the statement is, if I take 2 distinct E8 times E8 theories, some different number of five branes, some different choice of flat connections and gauge algebras, and I put them on a circle, maybe turn on twists, maybe not, maybe turn on Wilson lines, I get the same 5D supersymmetric quantum field theory. And I'll sort of, if I can hopefully get to it, I'll show you how just looking at this gives us some nice structure between the E8 times E8 theories that we started with. It sort of arranges these theories into nice orbits of duality orbits, which have some structure which we actually don't know yet, but yeah. Good. So
can I ask just a question about the previous slide? What does the superscript 1 indicate in the K? So I thought it was the twist, but then you twist when you go to 5D.
Yeah.
And you have a twist in 6D.
Yeah, I mean, I think this is not great notation, as you say. I mean, this is in 60, it's not twisted in 60, right? I mean, you can only twist it once you put it on a circle.
Okay, so there will not be a 6D theory labeled by some other thing.
Sorry?
There will not be another 6D theory where this superscript will be 2 or 3, or...
Oh, no, yeah, no, that's not possible, right? Because to twist, I need to go onto a circle.
Sure.
Yes.
Okay, thanks.
Good. Thank you. Yeah, good. So Right. I think this was someone asked about the conformal matter theories earlier. So this is sort of maybe addresses that question. So a nice construction of the E8 times E8 LST is also in terms of two different kinds of, is also fusing two different kinds of SCFTs. So let me sort of explain this construction because this will be useful for the results that we have. So of course we have the Orby-Instanton theories, which are an SCFT, which actually are just this, which arise from this system where you have an M5 brane, probably an M9 brane, and this is what's known as an Orby-Instanton SCFT. And so we'll consider rank 1 theories. So there's only one M5 brane probing some, again, ADE type singularity. And so if I pick this, this flat connection, so this mu1 to be trivial, I get the following quiver. So this is just a one curve with this gauge algebra here and the full E8. And if I choose non-trivial mu1s, I get breakings of this E8. And so the other kinds of SCFT that we'll consider are, of course, the conformal matter theories of rank M-2, which again now arise as these stacks of M5 branes just probing the C2 mod gamma G type singularity. And this is again an SCFT, which has the following quiver description. And so you can probably see where I'm going with this. You see this one here, you see this 2, 2, 2 here, and then if I put another one at the end, I get an LST. But the precise statement is that you basically you take two distinct Orby-Instanton theories here, right, with some mu1 and mu2, some singularity G. You basically gauge along the diagonal G when you fuse these two theories here and these two here. So there's a global symmetry G for both of these, right? And then you gauge that and you couple it to a tensor multiplet, such as to cancel the anomaly of this new gauge symmetry. And so once you do this, this new theory is an LST. So this construction is useful because the Orby-Instanton theories are actually classified, as I mentioned earlier, by Frey and Rodelius in 2020. And of course, the conformal matter theories are just, other than, M is the only parameter, then they're obviously fixed. There's obviously a finite number once you fix M because there's a finite number of ADE singularities. And so then the statement is that there's only a finite number of theories for fixed M and G. And so if what I said earlier is true, that you can have dualities between E8 times E8 theories, then the question one can ask is that how many of these E8 times E8 theories that you start with are actually unique up to T-duality? So can I take two E8 times E8 theories, put them on a circle, turn on data, and show that they're actually the same theory in 5D? And the structure of this, as I will show you now, is actually very turns out to be very rich. Good. So now just a couple of slides on the geometric construction, because if I go into detail here, it might, it will be another talk. So yeah, you can take so you can obviously construct supersymmetric quantum field theories from compactifications of F theory on non-compact elliptically fibered Calabi-Yau threefolds. Of course, this gives you some supersymmetric quantum field theory, but if you want heterotic little string theories, you pick the base of the fibrations to be P1 times C, or birational to P1 times C. And this now fixes for you, this P1 gives you the zero curve, and then this fixes for you the minimal condition for an LST. And then, as was first shown by Aspinwall-Morrison back in '97 in the heterotic string, how they basically showed that F theory can tell you the T-duality between the E8 times E8 and the SO32 heterotic string. Basically, if I take this Calabi-Yau, I can split it up into a torus and a base in different ways, right? There's no reason why a Calabi-Yau needs to have a single elliptic fibration structure. It could have many different. And the statement is then that these different fibrations basically tell you that the 260 theories are T-dual. And one can, there's a longer derivation for this, but I think the simplest way to state this is in terms of MF duality. So you know that F theory and F theory on a Calabi-Yau threefold is via MF duality is M theory on the same Calabi-Yau. And so so from this inequivalent this statement, you know that these theories lead to the same 5D theory. And the reason for this is that in F theory the torus is not not physical, right? You don't have Kähler parameters associated to the torus that affect your physics. But in M theory, once you put it on a circle, going from one fibration to the other is just a movement in the Coulomb branch or the Kähler moduli space. So that's why these two theories are dual in 5D. And so this is essentially the construction we use. You basically write down Calabi-Yaus, write down the different LSTs that you get from these Calabi-Yaus, and then the different LSTs that we get from these Calabi-Yaus corresponding to these different vibration structures. And then we look at the T-duality invariant data that I mentioned earlier, which is now just some geometric data. And we match these and say, okay, these are just beyond just the numerology of matching the data. These are actually T-dual because they come from the same Calabi-Yau. And in all our examples that we consider, it's always the case that the T-duality invariant data matches as we expect from field theory. So we don't have an example yet where you have two LSTs in the same Calabi-Yau, but their invariant data doesn't match. So it seems as though these necessary conditions might be sufficient. Good. So yeah, let me now just basically give you a picture of this. So this is one fibration for some Calabi-Yau X. You split the Calabi-Yau into a base and a fiber part, and you have some curves, and you have these fibers, and they degenerate at some points, and of course these lead to Cade symmetries, matter, and so on. But for the same Calabi-Yau, you can maybe split it into a base and a fiber in a different way with different degeneration structures, with different curve structure, with different base configuration and so on. And the statement is that these two distinct 6D LSTs that you get from these two Calabi-Yaus are the same on a circle. And so in some sense, you can think of this as a geometric proof of the duality. Good. All right. So now let me just give you, in the last hopefully 10 minutes, I can sort of give you some of the cool things that we have. Good. So as I said, it seems as though that the invariant data might be sufficient. So let's just start from that. So let's just try to see how you can match the data for different E times E LSTs, and then we construct the geometries. And this is precisely what we did. We matched the data, and then we construct the geometry as a sanity check to prove the duality. So if I have some heterotic little string theory with some singularity G and some number of fibranes, and maybe I can also twist by some discrete symmetry of order n, but I keep the flavor rank fixed, because of course we know that the flavor rank must match for any duality. The Coulomb branch then goes like this, and the kappa R, which is the other invariant, goes like this. Kappa P, of course, I told you that is 2 for heterotic LSTs. We are not considering base twists right now, so let's not consider kappa P equals 1 case. So right now, the only invariants that really matter to us are the Coulomb branch and the kappa R. So once you write these down, these coefficients C2, they depend on the singularity. These coefficients, these constant shifts in C1, R1, they depend on the flat connection you chose to the flavor symmetry, essentially. And then, I mean, these coefficients are known to be basically some group theory quantities given here, associated to G for untwisted theories. And once you twist them, you can easily determine them via some field theory analysis, which is what we did in our 2024 paper. And you can also basically just find the C2R2 for twisted gauge algebras. What's interesting is, of course, that kappa R and kappa P are not modified under outer automorphism twists. So the twists of these gauge algebras, because the dual Coxeter number doesn't really change under a twist. So that's what really kappa R depended on. So now one can ask the question, when are two theories, two distinct E8 times E8 theories with some different twists, some different number of five-branes, and everything like the flat connections and the singularities are also different, when are these dual? So essentially it just comes down to looking at solutions for these equations for different cases. So one of the cases is, of course, if you just keep the number of five-branes the same, and the coefficients also match for different values of mu1, mu2, and mu1 dash, mu2 dash. You might expect that these theories don't exist, but they actually do. These examples do exist. And the other case that you can look at is, okay, what if I shift the number of five-branes on one side by some constant? Then you have to solve this set of equations, and we find that there are solutions to this set of equations as well. So again, the reason this is possible is because we have this classification of Orby-Instanton theories for we have this classification of Orby-Instanton theories from Frey and Rodelius, and so we can just look at the list of the theories and go from there. So then obviously one can then ask, what are the possible solutions for G and G prime with some twists, possible twists? So the first solution, which was kind of a surprise to us that these solutions even exist, is that if you just fix the singularity, right, to be the same on both sides. So basically we call this kind of duality internal duality because it's for the same singularity. And let's just for now focus on the case where there are no twists. So these are just untwisted singularities. On the circle, I don't turn on any discrete holonomy. It turns out that the twisted theories actually just naturally find their way as a part of these as a part of these duality orbits, as I'll also explain. And so the question is, do such internal dual theories exist? And the answer is yes, which basically means that you have E8 times E8 theories in 6D that are dual to each other. They have different they have different choices of flat connections, i.e. different flavors, same rank but different flavors, and they're dual up to some shift of M. That shift can also be 0. So let me just give you now an explicit example in terms of quivers. So let's consider the E7 singularity. If I consider the E7 singularity, I choose trivial flat connections. I get this at rank 16, right? The flavor rank is 16. I get this full quiver, right? This is now the full tensor branch, where you can see now it's not just 1, 2, 2, 1 because there was these M5 branes fractionated. Now I can also consider the other E8 times E8 theory with a different flat connection, which then breaks this E8 to SO16, which still has the same rank. I can consider this theory as well, where I break the other side. And then I can also consider this one where I break to E7 times SU2 on each side. And it turns out that these theories, if you just compute the matching data that I mentioned, these theories are dual for this choice of 5 branes. And okay, you might say, okay, this is just numerology. You can just count this data and maybe it's the same. That doesn't mean it's dual. And of course, we obviously didn't stop there. We then constructed all these 4 theories as part of the same F theory geometry. So we constructed the geometry that gave rise to these theories as different elliptic vibrations. So that was a good check of the duality. Okay, so this is one class of theories. So, but you also have, of course, I can of course write this theory down as well, where I have the SO16 here and the E7 times SU2 on the other side. And the other theory that's left is the E7 times SU2 and the E8 on this side. And it turns out that these theories are dual to each other as well, where their 5 branes are related in this way. So it turns out that at singularity E7, at full rank, there are only 2 distinct duality orbits. So you only have 2 theories that are inequivalent up to T-duality. So at maximum flavor rank, we find that there are only 2 duality orbits, considering assuming that it's not an assumption because I mean in principle the number of Orby instantons are classified by Rudelius and Frank. So now for the other singularities, we did the same thing. This was for E7, we did the same thing, and we find that the number of orbits are given here. So for SO8 and SO10, you can see that, I mean, we didn't do the full D4 and the D4n plus 2. We are checking this as we speak because the number of Orbi instanton theories grows very rapidly at higher rank of D type. And so you can see the structure here, and if you look at it, stare at it a bit longer, you see that the number of orbits seems to be related to the order of the center of the singularity. But you may ask, of course, that this SO8 has Z2 times Z2, so that's not the order of the center. But there's evidence to suggest, and particularly in this paper here, that in these 60 theories, because the center is related to this one-form symmetry, this other one-form symmetry, not the one that I talked about. They show in this paper that really, once you take care of this particular anomaly, they show that really only a single diagonal Z2 survives the anomaly. So there is good reason. I mean, that was for SCFTs, so maybe take it with a big grain of salt, but I have checked this for LSTs as well. And if you take that anomaly into account, really the one form symmetry that survives is only related to a single Z2, not this Z2 times Z2. So there's good reason to believe then that it makes sense that there's 2 orbits rather than 4 here. And so we have checked for I think we've checked up to SO20 for D4 type, D2n type. And there at rank 16 at least, we again find 2 orbits. And here I think we've only checked SO14 beyond this, and that has 4 orbits. So we're still checking, but it seems as though there's some relation here, which we don't really understand. But it would be good to see why this is happening. And finally, you can ask what happens at lower flavor ranks, right? This is rank 16, that's fine, but what happens when you go to lower ranks? And it turns out that sort of the number of orbits there is there doesn't seem to be there doesn't seem to be a nice pattern like this. So it would be nice to figure out how the number of orbits changes as you go to lower flavor ranks. In particular, they grow very rapidly. But of course, this is still useful because for example, for SO 12, I think we've about 100 duality orbits, but there's like 10,000 theories. So having duality orbits, of course, still gives a structure to your E8 times E8 LSTs. Right. So I think, yeah, let me just quickly go through this. I told you that sort of these twisted theories somehow find a way into our discussion, and the reason is actually is contained in our work from 2024, is that using this matching of the T-duality invariant data, one can show that a twisted singularity of this type is actually dual to a untwisted singularity of this type in the E8 times E8 picture. For as long as the ratio of the number of 5 branes on both sides is related to the order of the twist. We don't know, of course, we don't know the reason for this. It's just something we find via the matching and via the geometries. And so you can see all twisted theories are dual to some untwisted theory. So basically, if I have the duality orbits for the untwisted theories, the twisted theories can just fit into those duality orbits. Of course, there is one class of singularity that is missing, which you may have noticed, is the SU odd type. Those don't have any untwisted singularity. So we should probably look into that more and see where do those theories fit in. But all the other twisted singularities are related to some untwisted singularity. And we show this via geometry as well. And just to add this twisted theory to the duality orbits we introduced earlier, this is the only twisted theory that you can actually write down that matches the data from the previous examples that I showed. So these are the twist is associated to this conformal matter chain, if you will. And this is your twisted 5D theory, and you can show that sort of this theory is dual each of these theories for I equals 1 or 2 finds its way into either of the two duality orbits that I introduced earlier. So again, yeah, these twisted theories they don't need to be considered. Most of them don't need to be considered separately. They find their way into these E8 times E8 duality orbits. All right, so just one last slide on some lower flavor rank stuff. So, right, so this is at rank 16, I told you these two theories are dual. Hopefully this isn't too small. I just couldn't fit it in the way I wanted to. So I told you that these are dual, but of course you can then sort of go to lower flavor rank, you can Higgs them. So let's do a particular Higgsing. So I basically blow down this one curve here, which takes the E8 flavor to the E7 flavor on one side. On this side, I just Higgs on some fundamental on the SP. I Higgs on that, and I break this to SP2. And so now the flavor SO16 breaks to SO12 times SP1, so rank 7. So of course, if you just look at these kinds of Higgsings, you see that the number of orbits should not change as you go from 16 to 15, right? Because these are still dual to each other. But the point is that these are not the only kinds of Higgsings you should do. And there are some violent Higgsings that you can sort of do that sort of go into the conformal, this conformal matter chain. And so we need to really understand how those Higgsings work to see how the number of duality orbits increases as you go down in rank. So that is something we're looking at now. All right. I went, I think, 7 minutes over time, which is not great, but okay. Let me just conclude really quickly. Yeah, so basically the goal of this work, or the goal of these past 2-3 papers, is to sort of look at to extend this T-duality landscape of heterotic LSTs and really see how much mileage we can get from just the matching of the duality invariant data. And it seems as though we can get a lot of mileage, as I've shown you. Like we can arrange these E8 times E8 theories into these nice orbits, theories that you may think in 60 are just like this bunch of different E8 times E8 LSTs. They're really, most of them are just the same. Well, not most of them. You can actually arrange them into nice categories in 5D. We found these dualities between E8 times E8 LSTs, leading to the structure of the duality orbits that I just showed you. So this includes twisted, untwisted, and so on. We also then, of course, as a check, which I didn't really talk about here, but of course I'm happy to talk after the talk about the explicit geometric constructions that prove these duality chains that we predict via this field theory data. Of course, now we need to answer some questions. So the first question, which I'm actually interested in, is the structure of the number of duality orbits at each flavor rank. How would they proliferate at lower flavor ranks? Then this other thing that we're also looking at, as I basically showed you a flavor of it, is what are the Higgs branch flows between the different duality orbits, right? Because they must be connected in some way, because all these theories are, at the end of the day, related by some Higgs branch deformation. Then you can also ask about the duality orbit structure for the SO32 LSTs, which we are also doing, and some of the results that I told you earlier about SO14, SO20 are actually from the SO32 side. But of course, we know that they should match on the E8 times E8 side, and so it would be interesting to map out the same structure but for the SO32 LSTs, where the duality will of course be very helpful. And then, of course, I haven't talked about base twists at all, like the twists of the quiver. So it would be interesting to see if we can include these theories in these orbits. And then finally, what are the implications for these dualities in lower dimensional theories? So there's a construction for little string theories. There's a construction for 4D SCFTs from little string theories. So there's a map between the T duality of the little string theory to the S duality of the 4D SCFTs. So what can we learn about the S-dualities in 4D theories from the T-dualities of the little string theories? That would be another thing that I would be interested in. But yeah, thank you for your attention, and apologies for going over time.
Thank you very much. Let's thank our speaker for giving a nice talk and also answering many, many questions. So don't worry about the time. Do we have more questions? Guillermo, you're already unmuted.
Yeah, I wanted to ask about when you don't have the geometric construction, is there a what ways do you have to make sure that these are true complete duality of the full theory as opposed to some infrared duality after the compactification? Is there any?
So I think, yeah, good. So I think if you believe MF duality, then this is sort of like this follows. So I mean, this is the technique that was used by Aspinwall Morrison in '97 to show that the SO32 the SO32 string theory is dual to the E times E8 string theory. They showed that you have this geometry which has these two different fibrations. One realizes the SO32 heterotic LST, not LST, heterotic string theory. The other realizes the E times E8 string theory. So yeah, if you believe that F theory and string theory are UV completion and so on, then yeah, then this should cover this should encode all the data that you need.
Okay, thanks.
Craig.
Hi. Yeah,
You have a hand.
two questions on a similar sort of theme. So in the you measure the size of the duality orbits.
Yes.
But inside of the duality orbits, you're writing things that are not dual to each other. For example, because you're not being careful about the distinction into the left and right M9 branes. So in what sense is this a duality orbit? The sense is that this is an orbit where the invariants that you compute are the same within that orbit.
Yes.
But they're certainly not dual theories, because there are theories in there that we can prove are not T-dual to each other.
Well, if these arise as distinct elliptic vibrations in the same geometry, then they are dual. Yes.
Perfect, but okay, I will come to this example in a minute. First, I was talking about the table, where you say that, say, for the SU, or B instanton, that this table.
Yeah.
So, for example, in each of these n orbits for SUN, you're grouping together things that are not dual.
When you say not dual, I'm not. I mean, is this back to the point that you were talking about earlier, where?
Exactly. This is back to what I was talking about earlier. So in that sense, we know they're not dual. Aspinwall Morrison tells us they're not dual, at least in the simple case where it's just the no gauge algebra. And in other cases, you can check in various ways by also computing the Higgs branch.
So are you saying that sort of like just matching the data is not enough, right?
Yeah, for sure.
Yeah, okay, good. Yeah. But I mean, yeah, regardless of, I mean, at least that's in my, from my perspective, like regardless of this thing that you're talking about the M9 branes, if I can realize these theories as distinct vibrations in the same Calabi-Yau, then they are dual, right?
Wonderful. So that's why I want to go back to the E7 example you were just showing me, where you said you had the geometry.
Yes.
Okay, so in this example, the dual, to make the dual, you need to say more than you're actually saying here. You need to be able to say how many on the left and the right are T-dual to the other example with how many on the left and the right. So you cannot just talk about M0 and M1, but you have to talk about sort of M0 left and M0 right, and M1 left and M1 right. Know that different distributions are not T-dual theories. So if you have the geometry, you should have access to the information of how many is on each side.
Right. I see what you're saying. Right. Yeah, I mean, I don't know if yeah,
So,
this
quick question: is the number of LSTs the same for both of these?
For both the orbits?
Yeah. This number is always
No.
the same, right? Like if
No,
this,
no, the number is not the
so
same.
then already you have a problem. Okay.
There's 4 here and there's 2 on the other, in the other orbit.
Can I maybe ask something related to this, which is hopefully
Oh, I see.
clarifying?
Yeah, go on,
Go
Paul.
on.
Great. Okay. Oh, sorry. So there's, I think like from the understanding what defines a little string and what the duality is. Yeah, I'm not exactly sure if we would agree on these 2 things. So let's say, like I think the cleanest example is the one at the very beginning, no? The E8, NS5 brains, and the SPN on the SO32 side. So the way how you, Craig, define a little string, which is fair in 6D, is roughly speaking by defining how many curves or you can shrink or pull them in the E8, now depending how you call this. So roughly speaking, you can define like a bunch of curves that you shrink to 0 size. So you go to a special point in the Kähler moduli space, in the tensor moduli space, and these different choices, you call those choices different little strings in 6D, right?
For sure.
Good. Which is fair. That's fine. But
Which is
the way.
And Rudelius, Bardwaj, and as well. I mean, this is
No,
not
sure.
An abnormal definition. They are different.
No. It's
different. So the point is that there exist multiple different contraction maps. So you can use this geometric construction to create different Calabi-Yau threefolds that engineer different quantum field theories in this case.
Good. So, but the point of this contraction map, whatever, I mean, is a map, is a special map that, or like the way how you, from the geometric point of view, the way how you define the little string then is by having like a geometry that describes this plus specific points, maybe maximal enhancement points in the Kähler moduli space of those. But the point is like the way how we define the T-duality is by saying that the 2 theories are T-dual when they correspond to the same Calabi-Yau with the same extended Coulomb moduli space, Coulomb branch moduli space. So whenever I can sort of recontract, like blowing up the curves again, I'm still in the same extended Coulomb moduli space, or extended Kähler moduli space. So these theories are still dual in the sense we are saying it. No, like all these different contraction maps that I've been chosen, I bring them all to the same tensor branch, say in 6D, and so they live in the same Kähler moduli space, and this is all we care about for the duality, because that would correspond to some Wilson line when you put it on a circle. So
this can for the duality, right? Because I mean, Aspinwall-Morrison tells you that the thing which is dual to heterotic is the thing where you put, I don't remember the numbers, maybe you put 16 NS5 brains on one side and 8 on the other, and not the thing where you put any other combination of them. So how can you be, you can't say the other theories are also T-dual, which seems to be what you want to say.
I mean, in the end,
a physical T-duality going on there.
I mean, it's you put the theory in a circle, you specify a bunch of data, which is the Wilson line, the continuous Wilson lines. That could mean, for example, bringing the theory on the Coulomb branch in 5D, and there the theory, modulus maybe a flop or so, which is just moving through a wall of the moduli space. There, the theory become exactly the same. And even if I have 100 different little strings just specified by different contraction maps, once I put them on a circle and allow for this extra piece of moduli that I am allowed to switch on, they would all go to the same 5D theory. And that I would call a duality. It's maybe just a way how you name things.
Semantics, but at least if we, with the consistency of Aspinwall-Morrison saying the 16 and 8 is the distinction, you want to claim the opposite. You want to claim that anything with 24 NS5 branes, regardless of how they're distributed, is T-dual because you can move the NS5 branes around. If that's the claim, okay. But still, I would want to know the numbers, the 16 and the 8. So in this geometric example that you write here, can you see the point where it's actually T-dual in the sense of you don't have to do this walk moving the NS5 branes around first, or the M5 branes?
Well, could well be. I mean, if you're sort of restricting yourself and saying, okay, I don't want to move, I want to keep it rigid, you're of course it could well be that you don't find any duality. Yeah. If you say I'm in this common huge moduli space and I don't want to I don't want to move anymore because I want to keep myself at these specific points, I will potentially not be able to reach the common point in the moduli space where the theories are in fact exactly the same. And yeah, then you would destroy the duality, of course. Yeah.
Right, but here you seem to be proposing there is a point where it exists, this duality, and I'm curious what that point is. It should be described in terms of how many M5 branes you put on either side. There should be a specific number, which is that point where you actually have the K3 that realizes the multiple vibrations.
Yeah, I mean the K3 is also always the same, and but I mean, for us the important thing is only that this point exists, that it's part of the same extended moduli space, and therefore in the 5D M theory on the, let's say on the most generic Calabi-Yau, let's say on the maximum Coulomb branch, on the maximum when everything is resolved in the smooth Calabi-Yau, is exactly the same. At this point, for sure, they are the same theories that you know. And from there on, you can go to two different 60 uplifts that you can, that is sort of the most generous way of defining the duality.
Sure. But but the 60 uplifts are fixed. They're not, you don't have this freedom of moving NS5 branes around, which it confuses me that.
Well, I'm not sure if the moving around means for you just shrinking a bunch of curves, because that you still have in 60. You still have the Kähler moduli space of the base, and then you can shrink stuff if you like.
Well, I need to have shrunk stuff. I'm not talking about an LST unless I have, let's say, a heterotic LST, unless I have a single compact curve which is self-intersection 0, say. So regardless of how I construct that, that's the LST.
Okay, good. Yeah, this you can. Yeah.
For me, this is an LST. Right. This
no,
is
that's fine.
Okay. So now I can take LSTs that I obtain by doing a contraction in two different ways. These are two different LSTs. And I would not naively say these two LSTs are T-dual to each other, even though all their invariants are the same.
Well, and maybe we have a bit too much of a coarse understanding here, but because, as I said, we define LST as the notion of leading to the same 5D theory, of putting it on a circle and being able to move in the modular space such that you reach exactly the same 5D theory.
I think what Craig is saying is sort of that we are fixing something canonically. We are fixing how many fibrins you are that are on the left or on the right or whatever. We are fixing that. We're just not like when you do the 60 uplift, that's fixed by our geometry. I mean, we haven't given you like I think that's what you're saying, right? That data should be somewhere.
Right. I think when you actually write down the K3s associated to these tensor branches, and the K3s at the point where they experience the T-duality should be at the point where you've contracted all of these curves to a single zero curve. And then you should see sort of what you've gauged on the left and the right.
Yeah,
so you should in the K3.
So maybe we can just quickly see if anyone else has some other questions about the talk, and then just continue the discussion afterwards. I'm very pro the discussion. Want to say on the record, just you know, maybe someone has something quick. Mario, you have a hand.
Okay, I had a question about this double elliptic vibration argument that just confused me, because when we do F theory and M theory on the same Calabi-Yau, in some sense, we are not really, there is a subtlety in my opinion, because to get to 5D, you have to decide what is the elliptic vibration and then send the volume of the elliptic curve to infinity.
Yes.
So if I have two options, I mean, I in principle have two different 5D theories to flow to, depending which one of the two curves I decide to send to infinite volume. In my opinion, I mean, that's a thing that I'm missing maybe with the constraint.
Yeah. Good. So you're saying because the 60 elliptic fiber is different, when I take the M theory limit, right.
Yes.
No, I think they should still. I mean, it's the same Calabi-Yau, right? So it should. I mean, I see from the physics perspective what you're saying is like there is some subtlety there, but in M theory it's the same Calabi-Yau. So I should be able to go from one vibration to the other in via Kähler moduli deformation, like Coulomb branch or Kähler moduli deformation. I see your point. There's a subtlety in the limit. There's
my intuition is that I decide to take away like a divisor, I will say, but in the two cases, I decide to take away a different divisor. If I choose one elliptic figuration with respect to the other.
Yeah, I mean, I see your point. I just don't know the subtlety off the top of my head. If Paul, do you have any comments on this?
Yeah,
or?
I'm actually a little bit confused by the question. Isn't it so first, I mean, what you have the geometry. It has multiple vibrations. You can put M theory on it. You can find the vibrations. There's geometric criterion to do so, and you can find different inequivalent vibrations in the same geometry at the same time. Just a geometric statement is good for you, no? But the limit where you take the volume of the elliptic curve in this type of adiabatic limit to infinity, this is the F theory lift, no? This is when you precisely do this. Then Vafa and friends told you that if I'm taking the volume of the elliptic curve to infinity, you grow the extra dimension and you actually go into 6D. So having your 5D theory, M theory on this geometry of a bunch of elliptic vibrations, and then I'm choosing specific infinite distance limits in the Kähler modular space that send precisely the elliptic curve to infinity, and specifying this direction in the Kähler modular space is the F theory lift. I'm not sure what's exactly the subtlety you're talking about.
Okay, maybe I was confused because I remember. Maybe I was confused. Okay, I will probably have to read better. Okay, maybe it was vice versa. I mean, my feeling was it was vice versa. But to go to 5D, I have to find the elliptic to infinity. But maybe I'm wrong. So that's the thing. Double check.
That's fine. Okay.
Okay. Thank you.
I have a general question, which is, yeah, I mean, anybody who can answer. If you take these little string theories, any of them, and then you compactify to 4 dimensions on a torus, so you keep the same theory, no twisting, and you then compute the corresponding Seiberg-Witten curve. Is there any information in the curve that could shed light on the little string itself?
Yeah, I mean, good. I think there should be, because I mean when you do the construction of these 4D, like you say, 4D SCFTs from the little string theory, there's a prescription where you see that the T-duality of the little string is actually the S-duality of the 4D theories. So I was talking about going from T-duality to saying something about the S-duality. You're kind of saying the opposite, right? So I think, I think there should be way to see that.
I see. So some form of electric magnetic duality would say something about the T-duality of
The little string.
Mhm.
Yes. But yeah, that would be sort of more richer than what I've talked about, right? Because I've only compactified on a circle.
Mhm.
Yeah, that would be more, that would tell us more about, yeah, that would be more richer to tell us about the T-duality, full T-duality group of the torus.
Has there been any exploitation of these? Any study? I mean, one issue is that yeah, some of those theories will be not yeah, the wrong side of asymptotic freedom for 4 dimensions, and so you could have maybe subset of them.
Ah, yes. Yeah, I'm not sure. I mean, the only exploration of this I've seen is a single paper. I forget the authors now, my apologies. Where they construct 4D n equals 3 from 60 LSTs. And they do this T-duality twist that you basically can't do if you just start from a 60 SCFT. So yeah, I mean, I'm definitely a proponent of, like, you know, using the LST to look at these lower dimensional theories rather than the SCFT, because apparently this T-duality twist gives you more freedom to get different theories.
I see. Mhm. Okay. Thank you.
Do we have more questions? Okay, so then I would say let's thank Hamza again. And we can go off the record.